Yeah, the rocket building business is filled with diverse ideas, and we're going to be looking at some of my favorite ones. To understand why there's so much diversity of thought in the new space industry, it's important to understand what SpaceX has done to transform the process of launching a rocket to space. Historically, rockets were built by governments with easy access to capital and cash, and they were built for the needs as determined by these governments. Weather satellites, GPS, exploration systems, and national defense. The process was long and often involved long, slow cycles of designing and testing the hardware and its subcomponents, often a very low tolerance towards undertaking risky approaches with the hardware, and a broad horizontal supply chain that involved a lot of suppliers across the nation. Now, this resulted in very limited access to space with extremely high amount of cost per kilogram, topping out at a whopping $50,000 per kilogram. And we're looking at you, Space Shuttle. But then came along Space Exploration Technologies Corporation, or SpaceX, founded by Elon Musk, and they turned the launch industry up on its head because they beat out all the odds to become the first private company to ever launch a payload into low Earth orbit in the year 2008. And over the past decade and a half, SpaceX has dominated and pioneered disruptive and innovative techniques like a Silicon Valley-like approach towards rapid prototyping, fast failing, and fail fast and fail forward on prototype designs to perfect the hardware, a high tolerance to undertake risky decisions since they're a private company, and a vertical integration strategy where SpaceX makes all of the components needed for the Falcon 9 right there in-house. And of course, who can forget those epic landings of the first stage of the Falcon 9? SpaceX has been the longest proponent of reusable rockets to bringing the cost of launching rockets way down, and they succeeded by bringing the cost of the Falcon 9 down from $10,000 a kilogram to about $2,000 a kilogram. What SpaceX has done here is they've successfully shown that with some diverse thinking, commercialization and eventually true democratization of spaceflight is possible, and this has paved the way for an explosion of new space startups that we're going to be exploring in this video. So let's start with Launcher Space. Launcher is an American aerospace company that is currently based in Hawthorne, California, and was founded in 2017 by Max Holt in New York City at New Lab. Max has a background in internet video streaming services and technology and is one of the founders of the live streaming service Livestream. Fundamentally, Launcher believes that optimizing for vehicle performance, i.e. maximizing and tweaking all of your variables to get the greatest amount of payload mass to orbit, will help them win the small satellite race. And they might be onto something here with their unique approach to engine design. The first rocket engine that Launcher ever developed is the E1 engine that was fed with kerosene and liquid oxygen propellants and generates about 2,200 pounds of thrust. But here's the cool thing about the E1 engine: blue exhaust Mach diamonds. Yep, you heard me right. The E1 rocket engine is spewing out these beautiful blue Mach diamonds because it's running very efficiently, almost at 98% combustion efficiency, which is unheard of for a kerosene and a liquid oxygen engine. So Launcher was able to accomplish this feat by utilizing advanced 3D printing techniques to bring the engine body in a copper alloy that allows for high heat transfer rate from the combusting of propellants and uniquely designed cooling channels because of this 3D printing process. They also cooled the rocket with liquid oxygen instead of RP1, which is kind of really cool and unique. Since the E1 rocket, Launcher is now working on their workhorse rocket called the E2. Side note, I love Launchers and Max Holt's naming convention. Max Holt started a company called Livestream because it live streams video. Wanted to start a company to launch rockets in space, call it Launcher. And you want to make a rocket engine, call it Engine 1 or Engine 2. And Engine 2 is the much larger cousin of Engine 1 and is powering their flagship vehicle, the Launcher Light. This is also a kerosene and liquid oxygen engine, and it generates a much larger 10 metric tons of thrust as opposed to the E1 engine, which only generates 2,200 pounds. The E2 engine is 3D printed with a unique copper, chromium, and zirconium alloy. And this is the diverse approach that's used by Launcher in order to achieve their high combustion efficiency that they do. Now, first of all, 3D printing rocket engines, there are very few companies out there that do that. And they've taken advantage of these unique capabilities and design freedoms that 3D printing really enables. Plus, they're creating a new supply chain that will enable future startups to one day take advantage as they roll in the lessons learned from investigating these 3D printing techniques. Second, and arguably more important, the entire chamber is printed with copper, chromium, zirconium alloy. Traditionally, rocket engines still use copper, and it's usually in the form of a copper liner. The liner is formed on a very complicated die-mandrel system and is forced into shape in a long, arduous process that is often expensive. But this copper alone lacks structural integrity, so there are metal jackets that are typically Inconel metal-based and are brazed or welded around the copper structure just to give it the right strength to handle the extreme stress of engine firing. Now, it's an involved process like I'm describing it, and you can imagine how much the cost meter ticks up. But it would be so much simpler if you just hit a print button on a 3D printer, and that's exactly what companies like Launcher are doing with a custom alloy based on copper, chromium, and zirconium to ease these manufacturing challenges and gain the benefits of the alloy. Copper is excellent in its heat transfer properties, as well as the structural benefits of chromium and zirconium allows the E2 engine that's cooled with liquid oxygen to give it its unique performance capabilities that Launcher is advertising will help them win the small satellite launch race. Now, I'll admit, liquid oxygen is an atypical choice for cooling the rocket engine because it requires an extreme amount of engineering precision, because the liquid oxygen can easily ignite in your channels. But Launcher successfully demonstrated this cooling capability with both the E1 and E2 engines, and this is a novel approach that's enabled them to achieve that high combustion efficiency of 98%. Best ever that I've seen for liquid kerosene and liquid oxygen engines. So you know what that means. Heavier payloads to space that will enable Launcher to be a serious competitor in this albeit crowded launch market. Well, that and those sweet blue Mach diamonds that I mentioned from the engine exhaust along the way as Launcher Light ascends to space. Next up, it's Pangea Aerospace out in Barcelona in Spain. And we'll talk about their regeneratively cooled Aerospike engine. That's right, I said Aerospike. Now, Pangea Aerospace was founded in 2018 by Adria Argemi, Javier Liaro, and Federico Rossi with a similar objective as most rocket startups, to lower the launch of rocket launches, to lower the cost of rocket launches to space, but also become a market-leading supplier of what they call disruptive propulsion technology, aka the Aerospike engine. Aerospikes aren't actually new technology. They've often been termed the holy grail of rocket propulsion because of their ability to direct exhaust gases in a more efficient way than a typical bell nozzle. The average bell nozzle has an expansion ratio, or the ratio of the exit area of the nozzle to the throat area of the nozzle, that is optimized for one particular altitude called the design altitude. This ratio is limited often by how large you can make the exit diameter of a bell nozzle based on the size of the rocket. So outside this one design altitude, the nozzle really isn't operating any differently. And that's okay, by the way. You'll learn on this channel that rockets are just giant engineering compromises. But an Aerospike engine can tip the scales of that compromise a little bit in your favor. The nozzle of the spike is as open as you want it to be, and the geometry of the spike allows for gases to expand optimally at every altitude. This in turn translates to a whopping 15% increase in efficiency, meaning you need 15% less fuel on your way to orbit. By the way, 15% less fuel doesn't necessarily mean 15% more payload mass to orbit. Remember the giant engineering compromise I talked about? But it certainly means significantly more payload to orbit than, say, your launcher with the traditional rocket engines. Well, if Aerospikes are so much better, why aren't they used on every single rocket? Makes sense, right? Well, because they were a pain in the manufacture. Well, at least with traditional methods of machining, milling, and other subtractive manufacturing techniques. The primary challenge of manufacturing an Aerospike lies with manufacturing that spike plug that you see and finding a way to introduce cooling channels to cool the plug as it works to handle the extremely hot temperatures of combustion, about 3,000 degrees Celsius. And again, the answer here for Pangea Aerospace was in 3D printing. Pangea and their 3D printing partner Anium have worked to solve significant thermal challenges of cooling the Aerospike by 3D printing the spike geometry in, you guessed it, a copper-based alloy called GRCOP42. This is a specially developed alloy, and not the same one that launcher is using, but it was developed by NASA and consists of a mixture of copper, chromium, and niobium. Copper is, if you remember correctly, is an excellent thermal conductor and conducts away heat, while niobium and chromium increases the strength of the material. Pangea developed novel geometries for the Aerospike, and they regeneratively cooled both the spike and the outer shroud of the engine. The spike is cooled by liquid oxygen, while the outer shroud is cooled by liquid methane. With extensive design and iterative testing, Pangea Aerospace has successfully test-fired this engine for over 3 minutes in a single firing to verify the feasibility for an Aerospike to perform these long-duration burns. And that's new and novel for an Aerospike in this day and age to see that level of test activity. The Demo P1, or their first demo Aerospike, has a maximum thrust of 20 kilonewtons, but Pangea already has a contract from the French Space Agency to determine ways to scale up this engine to a thrust of 1 million newton, and that's almost big as a SpaceX Raptor engine. And imagine that size of an engine. That's an Aerospike on, say, a Starship. That'd be pretty cool. Okay. This next one, I don't even know how to explain this idea to you all, because this is one of the craziest or the most diverse idea I've seen. And that award goes to Spinlaunch from Long Beach, California, because they want to launch a rocket to space by spinning a centrifuge really fast and flinging a projectile out so fast that it nearly has the energy to reach orbit. I know that's a lot to take in, but bear with me. This roughly 7-year-old company has completed multiple suborbital test flights using their centrifuge. At the core of it, a spinning kinetic mass accelerator can theoretically launch a rocket to space. Spinlaunch intends to use this principle by tethering a small rocket to a motor at the center of a 300-foot wide vacuum-sealed chamber. The rocket would then be spun up to about 5,000 miles per hour and then precisely released at the moment when the centrifuge has built up enough energy to fling the system out to where it can attain a velocity close enough to get to orbit, after which the rocket's going to fire its upper stage engine and eventually get to space. However, Spinlaunch has their work cut out for them, because there are going to be significant challenges with this system. The big one being that a centrifuge would have to exert up to 10,000 Gs of force on the rocket and the satellite inside it to get it up to velocity. And that would mean it would probably be torn to shreds. Spinlaunch, to their credit, acknowledges that this intense G-forces are an obstacle and has been evaluating the viability of various commercial off-the-shelf hardware to withstand this environment, alongside doing their own design and testing of hardware that can survive these intense loading conditions. And we haven't even talked about the actual size of the orbital centrifuge needed. Centrifuge that Spinlaunch is currently using is already the largest vacuum chamber in the world by means of diameter. Making an even larger centrifuge that pulls and maintains vacuum consistently for long periods of time will be a huge power challenge. Look, I don't know the math behind all their equations, so I don't want to needlessly diss them. Hey, many people said the same about SpaceX when they tried to, when they declared their intentions to make the Falcon 9 a reusable vehicle, with the first stage retropropulsively landing on a barge in the middle of the ocean, and people thought they were crazy. And look where we are now. And finally, let's talk about Relativity Space. Relativity was co-founded by Jordan Noon and Tim Ellis, former SpaceX and Blue Origin employees, with the goal to 3D print an entire rocket. That's right, 3D print an entire rocket. The entire thing will be 3D printed. Engines, tanks, inner stages, payload fairings. Well, bearing fasteners, because without fasteners, you'd be screwed. Relativity is uniquely poised to disrupt over 70 years of aerospace with the first fully autonomous software-defined factory for launch services with large-scale 3D printers that are continually evolving. And the star of the show here is Stargate. Stargate is Relativity's prized 3D printer, and that system has enabled Relativity to vertically integrate artificial intelligence, robotics, and a patented autonomous manufacturing technology. 3D printing an entire rocket is really hard, so Relativity does have its own material science team that has developed custom, high-strength, unique alloys specifically for Stargate. The material science lab also ensures it meets the highest quality of material strength standards that aerospace often requires, including their flagship rocket, Terran 1. Now let's talk more about Stargate, because that's a really cool system that I'm excited about. This large format 3D printing system is entirely software controlled. They have advanced machine learning and artificially intelligent driven controls, where Stargate's actually able to continuously monitor and vary and optimize the size of the print characteristics as needed without ever having to change any expensive tooling. This can all be done with software code. Traditionally, rockets have over 100,000 parts, and with 3D printing, Relativity is fusing artificial intelligence, robotics, and machine learning to reduce this part count down by 100-fold. And that's just about 1,000 parts in total on Terran 1. Relativity has real hardware at their launch site right now at Cape Canaveral in Florida. And that's their low to medium lift rocket, Terran 1, which is entirely 3D printed. They've successfully completed multiple rounds of qualification testing at sub-assembly levels for this vehicle. And Terran 1 is currently tracking an orbital launch attempt at the end of this year. And while Terran 1 is out there on the pad, its big brother, Terran R, is being designed as a fully reusable and a larger version of the system. A fully reusable Terran R is a diverse standout among the field of partially reusable and expendable vehicles in this medium and heavy lift market that Terran R is targeting to serve. Relativity is also the second company with a mission to make humanity a multiplanetary species. Their long-term mission remains to build an industrial base on Mars and help make humanity multiplanetary, like the mission of SpaceX. 3D printing is a core technology that needs to be perfected here on Earth so we can print anything we want on Mars, because it's going to be challenging to haul a giant habitat over to a planet with very little known resources. Look, some of these approaches we've talked about today are new, diverse, unheard of, risky, and has a lot of investor capital involved. But I would personally love for everyone's bets to pay off, because a healthy marketplace for rockets is filled with diverse and fresh ideas and out-of-the-box ideas that no one's ever heard of and people think are crazy, but 10 years down the line, who knows? And we only talked about 4 rocket startups trying different ideas to launch a commercially viable rocket business. There are so many more in the space industry, and that is the most exciting thing about the new space era right now: diversity and innovation. And that's the end of this episode. Check out the links in the description if you want to learn more about Aerospikes or the super cool Veritasium video about Relativity Stargate 3D printer. And hey, we need to make a part 2 or even a part 3 for this video, because there are so many more rocket startups with more diverse approaches that we need to talk about. Comment down below on some startups we should explore in part 2. And before you go, be sure to hit that subscribe button so you get notified when the next one drops. Thanks for watching, and remember, it's just rocket science.